Okay, hello. So we will start in 5 minutes. Okay, so it's about time. Thanks a lot. So thanks all for coming. So let's start the quick summary of the lectures this week. So actually, this is something that I have missed last time. So I should have talked about this problem last time, but never mind. So we do it today. So here, suppose that we have n distinct kinds of objects, and then each one of them, they have unlimited supply. Then we want to select our objects from them. So we will say that the number of ways to do so is n plus r minus 1 choose r. So why is it true, or how it is true? So for this one, you can imagine that so we have r balls in total, and then each one of the, so these balls are all what? So these balls are all just balls. They are not distinct balls. Okay, but then we can pick one of the colors for the balls, so that altogether we may have 3 red balls, 5 green balls, 7 yellow balls, and so on and so forth. Okay, so how many different ways are there for the combination, so that the total number of balls is r, and the colors that we can pick is there are n different types. So this also corresponds to the case where we have n variables. Let us call them x1, x2, x3 up to xn, such that each of these variable, they are an integer, a non-negative integer, so they can be 0, 1, 2, 3, and so on and so forth. So we want to ask how many ways are there such that x1 plus x2 plus dot 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 up to xn is exactly equal to r. Yeah, this is the same as how many ways are there to distribute our balls into n different colors. And then the way that we show this, so we will also talk about this later, is we can easily show this by using a ball and stick model. So you can check the slides for details. So we have these two examples. So they're just, you can just go through this easily at home. Okay. And the other one is another scenario. Suppose that we have n objects, and then they are all not all distinct. But we know that out of these n objects, Q1 of them are of the first kind, Q2 of them are of the second kind, and then Qt of them are of the tth kind. And then for this case, we want to select one or more objects from them. So how many ways are there to do so? Okay, so let us drop the case that we need to select one or more. So the number, so the number of ways to do so. So let's see. Okay, so for instance, for the first kind of object, there are Q1 of them. So in that case, we can select 0, select 1, select 2, up to select Q1, all the objects of them. So there are Q1 plus 1 ways of doing so. And after that, we will select what are the objects of the second kind that we want to have. So there are Q2 plus 1 ways to do so, and so on and so forth, up to Qt plus 1 ways to do the selection of the objects of the tth kind. But then why do we want to have a -1 here? Because for this part, it has a case that we are not selecting anything of the first kind, not selecting anything for the second kind, and so on and so forth. So in this case, there is one of them represents the way that we are selecting nothing. So if our problem is to find out the number of ways to select at least one object, then we need to deduct 1 here to take away the case. But in some of the example, then we don't need to take away this -1. For instance, in this example, so we want to ask how many devices does 1400 have? So this is a primary school question. So when we are at the primary school, we will try to list out all the devices of 1400 one by one, and then we count them. But on the other hand, if we just need to find out the number of devices, then it can be done fairly easily, because we can have a prime factorization of 1400 as in this form: 2 to the power 3 multiplied with 5 to the power 2 multiplied with 7 to the power 1. And then we know that if it is a divisor of 1400, then we may be having some 2's inside, but then you cannot have more than 3 of them. It may have 5 as a factor, but it cannot more than 2 of them. And it may have 7 as a factor either, but it cannot have more than 1 of them. So in this case, the number of divisors of 1400 will be equal to, there's 4 ways to choose how many 2's that this divisor has. So 4 ways here, yeah, because we can choose 0, 2, 1, 2, 2, 2, and 3, 2. And then 3 ways for the selection of 5, and 2 ways for the selection of 7. So in that case, there are 24 ways. We don't need to do the -1, because the case that we are not selecting any 2, not selecting any 5, not selecting 7, it represents the number 1. Okay, so 1 is a divisor of 1400. So there are 24 of them. Okay, another related question. So here, suppose that we have n given ways, and then we want, so this is like when we are measuring, so we are using a balance to measure the how heavy an object is. So we can put the weights on one side, and then the object that we want to measure, how heavy it is on the other side. So suppose that we have n distinct weights that we can use to n pieces of weights that we can use. So how many different amounts of things that we can measure on the right hand side? So the maximum number is never more than 2 to the power n. The reason is that because we have n pieces of weight, then we can, for each of these weights, we can either use it or not use it. So in that case, there are 2 to the power n ways for the combinations of the weights that we are using. So we have an upper bound. But it all depends on what kinds of weights that you are using. Yeah, maybe you are using weights of the same type. All of them are of, let's say, 1 unit. Then in that case, yeah, then no matter how you do the selection, you can't have 2 to the power n. You just have like something like n plus 1 different weights that you can measure. But a related question here is that suppose that this time you can design the weights that you are going to use. And then our target is to measure the objects whose weight is an integer weight between 1 to 100. So the objects that we have here could be of 1 unit or 2 units up to 100 units of weight. Okay, so in that case, is it possible to design the pieces so that we can measure any combination of this? So in that sense, we don't need a lot. We just need to have, let's say, 7 different pieces, and then each of them is of weights starting from 1, 2, 4, 8, 16, 32, and 64. So we have these 7 pieces, and then we know that we can make use of these pieces to get any number from 1 to 100. So in that case, yeah, we can solve this problem. And now, so okay, back to the previous slide. And then we know that this is an optimal scheme because we are using only 7 pieces. Yeah, we can never use only 6 pieces because 6 pieces can only measure up to 64 different kinds of weight. But here we need all possible scenarios starting from 1 to 100. So we need at least 7 pieces. And then associated question here is that now suppose that on the balance we can put the weight on either the left hand side and also the right hand side. So we may for instance we may design 2 weights of weight 1 unit and let's say 3 units. So we have a 1 unit and a 3 unit. Based on them, I can measure 1 just by using the 1 unit piece. I can measure 2 by putting 3 on the left hand side and 1 on the right hand side. So I can measure 2. I can also measure 3 because I'm just using the 3. And then I can also measure 4 because I'm using 1 and 3 together. So in this case, using just 2 distinct pieces, I can measure up to 4 different possible combinations. So in that case, we want to ask, okay, how many different amounts that we can weigh when we are using n pieces? And then similarly, from 1 to 100, yeah, so can you design a scheme, an optimal scheme using the minimum number of pieces? Okay, so this is an interesting question. So we have the solution in the lecture, but then yeah, it's good to think about this. Okay, so this is the first set of lecture slides, and then we are going to the next one. Okay. Yeah, again, yeah, I'm sorry that if I'm speaking very quickly. So if you want to, so this is only a summary. So if you want to know about the details, yeah, please go to the OCW recording for it. Okay, so now for combinations and permutations, we will talk about a very closely related problem called distribution of objects. Okay, so here, apart from counting the number of ways of selecting things or arranging things, so we may sometimes come across the problem of distributing objects into positions or into boxes. Yeah, so there are actually at least 12 different kinds of interpretation of distribution of objects into boxes, because maybe the objects that we are selecting, they could be distinct objects or non-distinct objects. So for instance, when we are maybe we are distributing identical balls, or maybe we are distributing distinct people around the area, something like this. And the positions itself, okay, we are putting balls, let's say, into the boxes. So the boxes could be labeled or the boxes could be unlabeled. So this will have different meaning. So here in this class, we will first look at the case where the boxes are distinct. So for the case of non-distinct positions, then we will talk about this later when we start talking about generating functions. So we have this topic, combinations and permutations. The next one will be generating functions. And then the next one will be recurrence relation. Okay, so distinct objects. Okay, so let's see different scenarios. Okay, so for quick checking of our understanding. So suppose that we have R distinct objects and then N distinct cells and boxes. Okay, now we assume that each box can only hold one object. So the number of ways, suppose that N is greater than or equal to R. So here we have more boxes than the balls. So, and then we have to use all the balls. We have to put all the balls into the boxes. So how many different ways of putting the balls into the boxes? So it is actually an arrangement problem. It is PNR. So we can interpret this in two different ways. So first of all, we can compute the number of ways fairly easily using the rule of product. Because the objects are distinct and the boxes are distinct, so we can ask a question, okay, where should I put the first ball? Okay, so there are n choice. And then where should I put the next ball? Then there are going to be n-1 choice after we have put the first ball, right? And then we have n-2 choice of how many ways that we can put the third one, and so on and so forth. So the number of ways of putting all the balls into the boxes will be equal to n times n-1 times n-2, where there are r terms multiplying together. So this is exactly PNR. Is that okay? And then, so on the other hand, we can also think about this as a permutation problem. So here, what we are going to do here is that, because finally we are going to select which boxes that we are going to hold the balls. So we need to select R of them outside to put for R of the boxes for holding the balls. Is that okay? So, and then after the selection of the boxes, then we need to assign which box should hold the first ball, which box should hold the second one, and so on and so forth. So it is actually the same as finding the number of R permutation when we have n boxes to choose. Is that okay? So this is PNR. And then the other case, it is a strange case. So this time, suppose that we have more balls than the boxes, and then this time we are not using all the balls, yeah, because there are so many balls. Okay, but then we want to fill up all the cells, so we need to make sure that each cell receives a ball. So how many ways are there? Then easily we can count it. This time this is PRN. Okay. And another scenario. Okay, suppose that we have R distinct objects and then n boxes, but then this time each cell, each box can hold any number of objects. So suppose that we also don't care the ordering of objects inside the box. So how many ways are there? Okay, then this is fairly easy. So for each object, we want to ask which box we are putting it to. So there are n choice for each object, and then there are R objects together, so it is n to the power R. Okay. Okay. Or alternatively, you can think of a representation that describes a certain way of doing so. So we can use a n tuple. Okay. So the first tuple specifies the location of the first object, which cell the first object is put into, so it is 1 to n. And then the second tuple is about where we put the second object, and so on and so forth. So we are counting how many tuples are there, such that each tuple label is from 1 to n. So it is, again, this time n to the power r. Okay. So it is sometimes very useful to think of a representation to describe the way, and then you count how many different representations can there be. So it is equivalent in counting the number of ways. Okay, another scenario. So this time, a little bit different from the previous case. So here, this time, we still have R balls. We still have n boxes. and then the box can hold any number of objects. But then this time, suppose that we care about the ordering of objects within the cell. So let's say which object, suppose that we are looking in the first box and then we have 5 objects inside. We care about which object is the first one to put in, which object is the second one, which object is the third one, and so on and so forth. So we care about the ordering of the objects inside a box. In that case, the number of ways of doing so is this one. This is n plus r minus 1 factorial divided by n minus 1 factorial. So how do we get this? So whenever we have a question like this, so always, don't memorize this formula, but on the other hand, see if you can find interpretation of what is going on. So we can have two ideas of those, so they are all getting the same result. So the first idea here is that, so I'm going to use, this is the so-called ball and stick model to represent the distribution of objects. So we have n minus 1 sticks here or bars here, so that between the bars they represent a box. So this is about the content in the first box, this is the content in the second box, the content in the third one, content in the fourth one, and so on and so forth. So here the first box, it contains first of all the orange ball, and then let's say this is the pink ball, and then in the second box it just have the green ball. The third one, it just have the yellow one. The fourth box, it is empty, and so on and so forth. And now, our problem here is that we have altogether R balls, and then we want to put them into these boxes. How many ways are there? So, to do so, what we can first think of it is let us find out how many ways that we can, let's say the balls are all the same. How many different distribution of objects that we can have. Then we have done that before, so this is actually something that this is going to be like a permutation of the bars and the balls. So it is going to be C n plus r minus 1 choose r. So we have a bit string, or we have r balls and n bars that we want to make the arrangement. So how many ways are there? So any arrangement corresponds to a way to distribute objects into the boxes when the objects are the same. And after that, we simply multiply it by r factorial to color the balls afterwards. So in that case, we get this result. So this is n plus r minus 1 factorial divided by n minus 1 factorial, r factorial here, multiply with r factorial. So the r factorial get cancelled. So we get this result. And then the other way to see this is we can start with an empty boxes everywhere. So we have just n minus 1 bars at the beginning, and then we are going to insert the balls one by one. So for the first ball, then there are going to be, because there are n minus 1 bars there, so the first ball there are n positions that it can be placed. For the second ball, then it can have n plus 1 positions that it can be placed. So in that case, it is n to the power r. n to the power r, but the power is a rising power, okay, of n to the power r. So it is n times n plus 1 times n plus 2, and so on and so forth, up to altogether there are r terms. And then again, we get this same result. Okay? So this is an example. So this is an example of the previous problem. So we have 7 flags and then 5 masks, and then all the flags has to be put on the mask. But then the ordering is also important, and then the masks are all different. So how many ways of doing so? So this is exactly the same problem as we are studying here. Okay. Okay, another example. So this time, suppose that we have n objects, and then Q1 of them are of the first kind, Q2 of them are of the second kind, and so on and so forth. And then we are going to use all the objects. And then the number of permutation, how many are there? So we studied this before. So previously, we used actually the rule of, it's not the rule of thumb, it's not the rule of product, but it's called the rule of quotient. Okay, so we start by thinking of all the objects are distinct from the beginning. So there are n factorial ways of arrangement for them. But then suddenly Q1 of them becomes the same. So in that case, we need to divide this by Q1 factorial. And after that, suddenly, Q2 of them, of the remaining, they become the same. So in that case, we need to divide it by Q2 factorial, and so on and so forth. So in this case, yeah, so we get this number. But then we can also have a different interpretation. Okay, so this is another interpretation. So this time, so we can think about, okay, so let's see. So this is n objects. So we want to use, because we are looking for arrangement of them, n permutation, right? So let us list out these objects and then put all the objects into n cells. These n cells is, let's say, putting from left to right, okay? And then we assume that each cell can only hold one object. So by placing the objects into the cells, this corresponds to a particular n permutation that we have. So we want to find out how many ways can we put the n objects into these n boxes. So this will give us the number of n permutations in total. Now, to get a particular permutation, what we need to do here is we need to select which boxes along these n boxes should hold the first type item. And after that, for the remaining boxes, which ones will hold the second type, and so on and so forth. And then, yeah, this is very easy. So there are n choose Q1 ways to select the boxes for the first objects, right? Select the boxes for the first type objects. And after that, we have only n minus Q1 boxes left, and then we need to select Q2 of them to put the second type, and so on and so forth. So in the end, yeah, by rule of product, the number of ways of doing so is Cn Q1 multiplied with Cn minus Q1 choose Q2 multiplied with this one, and so on and so forth. So this is this number. And then, yeah, because we now know the formula for CNR, so in that case, we can plug in the formula for each one of them, and then we see a lot of cancellations, and finally, we still get this result. So this is a different interpretation of the same thing as we studied before. Okay, now a little bit different. Okay, suppose that this time, we only have R objects. Okay, and then each cell can still hold only one object. So how many ways of distributing the objects into the cells? So in that case, yeah, this is actually the same problem as before, except that we can make it the same. The previous one is we have n objects, we put them to n boxes, and then here we have R objects, we put them into n boxes. So we can imagine that we can invent a new type of object called empty object. Okay, so we have n minus R of them. This is the last kind. Okay, so the same problem is, if we put in these n minus R objects, new objects into here to consider them together, then we have the same result as before. So in that case, it is n factorial divided by this part where they sums up, where the Q1, Q2, Q3 up to Qt sums up to R, and then finally we divide this by n minus R factorial. So you can check about this at home later. Convince yourself why it is correct. Okay, and as for non-distinct objects, so suddenly now all the balls are now the same. So previous case, balls are distinct, so it is like a permutation problem. And now when balls are not distinct, so it is like a combination problem. So when we have R non-distinct balls and then n cells, each cell can hold one object, then what does that mean? So in that case, some of the cells, yeah, so we assume that n is greater than or equal to R. So we want to find out how many ways are there that we can put all the objects into the boxes. So here, we just need to see, because balls are the same. So here, we just need to select which box will be used. So there are n choose R ways. And then the next one is just a silly problem. So you can go and find out the answer for yourself. And this time, so here we have limits on the number of objects that a box can hold. but then here we don't have any limit. So suppose that the number of objects in a box can be any number from 0, 1, 2, 3 up to whatever. Okay. And so again, we have R non-distinct objects, and then we want to put them into n cells. So how many ways are there? So in this case, it is n plus R minus 1, choose R. So this is the same as this problem. Yeah, this problem, except that the balls are not colored. So the number of ways of doing so is, yeah, we don't need to multiply the R factorial in the end. So we get this result. So it is this one. Okay. A slightly variation of the problem. So here this time we have an extra requirement. So each cell must hold at least one object. So to begin with, we need to assume that R is greater than or equal to n. So we have more balls than objects, and then we have more balls than the boxes, and then we require each box must hold at least one ball. So how many ways of doing so? So because we have this requirement, at least one object to begin with, so the answer is fairly easy to derive based on the previous understanding. So what we need to do here is that we just put one ball into each box at the beginning, and then forget about them because they are now there to satisfy each box hold at least one object requirement. After that, after we put one ball into each box, okay, then we are getting back to the same setting as before. Each box can now hold any number of objects when we are distributing the remaining balls. So how many balls we have? We are now remaining. We have R to begin with, but then we have one ball for each box, so there are only R minus n balls left. So by plugging in the number of balls changing from the original R to R minus n, so we will have the answer will be Cn plus R minus n minus 1, so which is going to be R minus 1, choose R minus n. Okay, so it's going to be R minus 1, choose R minus n, or equivalently, it is R minus 1, choose n minus 1. Okay, so go home and find out why it is correct. So we have examples here. Yeah, you can go home and check. This one is interesting. So for this case, yeah, this is the problem. So suppose that there are two n plus 1 seats in a congress, and then these seats are to be divided among three parties. So let's say the party A, party B, party C. So so collectively, we don't care the people in each party. So we just want to find out, oh, how many different scenarios can there be? Maybe party A has 3 seats, party B has 7 seats, and party C has 12 seats. So 3, 7, 12 is one possible way of dividing the seats among the three parties. So we want to ask, so how many ways are there so that some party will obtain a majority of the seats? Now, if we can find out this one, then we can easily calculate how many ways such that nobody has the majority. So which means what? Which means that any two parties together combined must ensure a majority of seats. Now, this is very interesting. So if you cover the hints here, if we start from directly answering the latter part, this may be a little bit difficult. But if you solve the first part, then it will certainly be much easy to solve. And hidden sense is that this is related to a problem about how many triangles are there. So suppose that someone tells you that, oh, we have a triangle. There are three sides, let's say x, y, z, whose length are all integers, and then they sum up to some number, let's say 17. Okay, so how many different triangles can you imagine will satisfy the condition? The sides are x, y, z in length, and then the total length is 17, and then each side is integer. Okay, so it could be 5, 5, and then 7. So this is a possible case. Or maybe it could be something like 4, 5, and 8. This could be another case. But then 3, and then 11, although they add up to exactly 17, but this is not a possible triangle because for a triangle, it must satisfy the triangle inequality. Is it the triangle inequality? Any length of two sides combined must be longer than the length of the third side. Okay, for any two, they add up to a number which is always greater than the third one. And this is exactly the same problem as we're studying here. Okay. Okay, finally, we have some extra interesting topics. So you don't need to memorize this. This is just for fun. So we will talk about something called the Stirling formula. Now, in our combination terms or the permutation terms, we will see n factorial or some numbers factorial appearing again and again. And then one wonders, is there a way to find out, to approximate the value of n factorial? Now, to compute n factorial, it takes order n time, right? So you get a number, multiply, so you get n and then multiply with n minus 1, multiply with n minus 2, and so on and so forth. So it takes a long time to compute the value, the exact value of n factorial. Is there a way that we can use, let's say, constant number of operations or log n number of operations so that we get a value close enough to n factorial? So this is the purpose of having the Stirling's approximation. So mathematician Stirling in 1730, he got this formula. So he found out that the value of n factorial is very, very close to the square root of 2 pi n. This pi is the 3.14 ratio, okay, between the length of a circumference to the radius or to the diameter. Okay, so this is the pi value. So square root of 2 pi n multiplied with n divided by e to the power n. So this e is the base of the natural log. Yeah, it's 2.8 something. Okay. So what does that mean? Okay, so Stirling says that n factorial is close to this number. Now, if you want to compute the value of this number, it is rather easy. You get n, you divide by e, so easy, constant time. You raise it to the power n, so it is like a power function. Yeah, you call it a power function once, but it can also implement by using log n multiplications, all the log n multiplications. And then this one, 2 times pi times n, so this takes constant time to compute this value and take the square root constant time. So to get this value, you don't need all the n time. It is easy. And then this term is much easier to do the cancelling or to do the estimation if you have other terms to consider together. So this is a very useful approximation. And by means of this approximate sign, what does that mean? So it doesn't mean that the two of them are having very close value in the absolute sense. It turns out that the value of n factorial and the value of this approximation will be differed larger and larger, more and more, as n goes to infinity. But the ratio of them, this one and this one, the ratio of them is getting closer and closer to 1 as n got larger. So this is an example. So if you are talking 1 factorial, the absolute error is something like 0.08, percentage error is 8. But when you look at a larger number, 100 factorial, if we are looking at the absolute error, it is this is a very large number, something times 10 to the power 154. This is an astronomical large number. But on the other hand, if you look at the percentage error, this is Stirling's approximation. This is the exact value. So they look really, really close to each other. Yeah, both of them are something like 9.3 something multiplied with 10 to the power 157. And so the percentage error is really, really small. So this is how Stirling is useful in the approximate in the relative error sense. Okay, the idea of getting this approximation is easy. Yeah, we need to use a little bit of our calculus to do so. The main idea is Stirling's formula or the term that we want to measure, n factorial or log n factorial, is closely related to this curve. So we have a curve y is equal to log x. Okay, we draw this curve, and then we use this curve to estimate the value of log n factorial. Okay, so log n factorial is equal to log 1 plus log 2 plus log 3 up to log n. And then this curve is y is equal to log x. So naturally, we are going to look at the area under the curve because it is going to be summation of a bunch of log x value. Okay. Once we have an approximation of log n factorials, then we can take the exponentiation of this one, so we can have an approximation for n factorial. Okay. So first of all, the area under this curve is something like this, and then we can have an estimation of this by using this trapezium. So it is the standard Riemann sum. Okay, that we start learning integration. So somehow, with the connection between the area under the curve here, the purple part, and this one, the pale blue part, this is the total area of the trapeziums, then in that case, we have a bound for log n factorial. Okay, so here we have actually an upper bound of log n factorial. And similarly, this time, this is about the trapezium, this is under the curve, covered by the curve. But here, if we consider the opposite case, when we look at trapezium that is covering the area under the curve, then in that case, we have another bound. So this time, by comparing this time, this purple part with the trapeziums here, the total sum of area of the trapeziums here, we get another bound. This time, we get another bound of log n factorial. This time, we have a lower bound. So the combination of them is log n factorial can be bounded above by a term to some area under the curve, and also bounded by another term. This is also some area under the curve. So in that sense, we find that log n factorial can be, so by rearranging terms together, it must be of this form, n plus 0.5 times log n. So this log, something like this. Doing something like this. So the way that we get something like log n minus n log n minus n, it is because this is how we solve this indefinite integral. So not indefinite, so this definite integral. So once we solve this, then we get something like this. So we have a bound for log n factorial, and then so that we have a term delta n here, which is not known. But we know that this delta n is less than 1 and greater than 0.893 coming from this part and this part. We have a 1 here, we have a 1.5 here. Okay, so after that, so we have this bound. So after that, after taking exponents on both sides, we get the formula n factorial must be equal to e to the power something multiplied with square root of n multiplied with n over e to the power n. So this part is what we have seen before, like Stirling's approximation, the main part. And then this one, it turns out that the value of this one is approaching to square root of 2 pi as n tends to infinity. So that's why we get the Stirling approximation. Now, as for how to get to square root of 2 pi, so in the past, I have listed as an interesting problem in your assignment. But perhaps for this year, I will, because you are all doing greatly in the studying, so perhaps next week's tutorial, if there are no particular question you are asking, I will give a very high level proof why this can be bounded by square root of 2 pi. Okay, but it will require some calculus, and then I'm not good at it, so maybe I'm making mistakes. So, but at least this is something that I can show during the tutorial next week. Okay, so actually that's all for today. I hope you are still doing well so far. And then again, if you have any questions, please ask me or the tutors, and then send us the through the question form, and then we will answer it as early as possible. Okay, that's all. Thanks a lot. Okay, thanks for coming.